Hello developers, let's start developing. Today we're gonna take on the 12th Advent of Code task, and it's basically some kind of a hill climbing algorithm that will do something. So basically we need to find a path from the start to the end according to some rules. The rules are relatively simple. We have a set of heights, so to say. A is the lowest, Z is the highest, and each time we can only go up to one higher. And that's the only rule that we can get. So from A we can go to any A or to B. From B we can go to C, to B, or we can go to A. That's no reason that stops us. Yeah. And if we're going from I don't know Y, that means that we can go to another Y or we can go to a Z, which is the elevation of the end, or we can go to any other letter. So basically, we can fall with impunity, but we cannot rise with more than one thing at a time. So I'm thinking that, and we need to find, of course, the shortest path. I'm thinking that a kind of a flat fill or something like that will take care of this. So, first of all, let's parse the input. Fortunately, this time we have a relatively simple input, and we know that S is actually an A and E is actually a Z. So we just can parse it into this kind of an object. So I will just say that input dot, let's have it like this, const map is an empty array, and then we can just do a for loop, a for of loop, so to say, for line of input lines, and then for each line, first of all, we need to have the indexes, so this won't work. We can use a simple map method as well. Yeah, let's do that. Let's have a map method that is gonna be a bit on the complicated side. So we have the line and we have the index, and the index is gonna be our y coordinate. So the y coordinate, and this is because the coordinates in matrices are kind of the reverse of what the coordinates are for regular geometry. So in regular geometry, I'm gonna use this kind of coordinate system when this element, let's say this element, in regular geometry is going to be 1x, 5y. But in matrices, this is the fifth row, second element. So in order to, so that I can think in these coordinates, I will basically invert the y and the x. That means I will use y as the index of the row over here. So we have the line itself and the index. And now for each of these, we will return a mapping. Yeah, we will split the line and map each character. And yeah, basically we're gonna do something like this. Once we split the line, we need to map it. We have the character and we have the x variable here. So if we have the start, and let's call this a maze. No, we cannot do that. Yeah, let's do something like this. This is not really efficient, but we don't need at least this because it can be inferred. So yes, have something like this, that if we find an S, start is an X, the X and a Y, and the character is actually not a dot, but an A, because we are starting on the A elevation. And if we find the E, then the end is that much, and the char is a Z. And now we need to return the character, but we're not going to return the character. And this we can just do without. We're not going to return the character, but we are going to return, just a sec. If we do it like this, so this ends here, and this is like this, and this is like this, and yeah, this works. So right now, if we put this as, for example, call this maze or map, actually, we can see that map is a string array, and we want it to be numeric because a plus 1 is not b, but 0 plus 1 is 1. So we will map everything, and we will want to do a mapping when we have something like a needs to map to 0. And that means that z will map to 25. So how do we do that? Well, we have a, and we can just do char code at, give me the character at the 0th position, and that gives me 97. What happens if I subtract 97? I get a 0. And what happens if I do the same thing for z? I get a 25. So we will use this thing to basically map it into a 0, 25 mapping. And now we can just return our maze, which has a start and an end and a map. Let's see what the input is. Yeah, I could have run in debug mode, but because we won't get to see the map, let's see if this does something. So we have that our start is at a position called how much is was a position called 0, 0. That is correct. And the end is in a position called 5 and 2. Remember that we are working in an inverted way. So 0, 1, 2 and 0, 1, 2, 3, 5. Looks okay. The heights, we have AAB, QPONM, AAB, and some values, and on the 102, when we have 0, 1, 2, 3, 4, 5. This is our end. We see that for the end, we subtracted z, and next to it, it's 23, which is an x. Yes. Okay. Seems like that we have our input covered. And let's see, A, B, C, A, B, D, E, E, F, G, H, I. That means that the last one should be 0, 1, 3, 4, 5, 6, 7, 8. Yep. Oh, we actually wrote map twice. I didn't thought that this will output the map as well. So now we can have a result. And the result is gonna be Let's see, we need to extract how wide is the map. It's the width of the length of the first element, and how high it is the length of the map itself. Yeah, so we're gonna create an array that has the height of our map and fill it with zeros, and then map and fill it with zeros again. So this will return a corresponding array that right now has zeros, and I plan to use this to store basically the distance, the minimal distance that we've gotten so far for any point on the map. So we can say, actually, I'm going to fill it with minus ones. Minus ones means that, or do we want to be fancy? No, let's use minus one. I wanted to put something like negative infinity, but minus one works just as well. Minus one means that we haven't visited that point as at all. We might now, we need to make a decision. How are we gonna approach our target? One way is to do it haphazardly. And to be honest, the input doesn't look so big, the big input, that we can just basically calculate it for every point on this map and then take the value from for the end. And that's what I will actually try to do. So I will put the start in the queue, and while we don't have a queue, let's see what this generates and whether it's what I want to do. And now it ran out of ideas. It is something similar, but maybe not exactly what I wanted to do. So we have a queue. In that queue, we're gonna put all the points that we can reach. And right now, I will set the result of the start, that we can reach the start in 0 steps, because we are at the start. Now I'm putting the start in the queue, and I will put all the points that we can reach directly from the queue, so we're looping here. I put the start in the queue. With the queue processing, I will take the first item from the queue, see all the points that we can access from our current point. And if they are not visited, I will add them to the queue. But don't really need that. Yeah, we need this current dot y, current dot x, and by the definition I gave you, I can guarantee that the current value will not be -1. It should be 0 or above. So we have the current value, and we can calculate the neighbors. These are the neighbors, and this is the best thing about Copilot. So we have 4 potential neighbors, and now we can see whether those neighbors are reachable. And actually, I'm gonna do it like this. Filter. Yes, that is the one filter that I want to do. This basically filtered out invalid neighbors because not every point has 4 neighbors. The corners points, the edge points don't have 4 neighbors. So here we are filtering the invalid neighbors. We're filtering neighbors that have an x that is Yeah, we are filtering in those that where x is larger than 0 or equal, x is less than the width, and y is larger than 0, and y is less than the height. Those are our neighbors. So, and those are our real neighbors, and I will also filter out those. This is the wrong filter. I will also filter out those whose not result but value is bigger than the current value. Oh, no, 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 no. This is map. This is not the result. We have two different things. We have input.map, which will give me the current elevation. Let's use the word from the program description, and we will have the current. Actually, we can call it the current result, which is this. So we have the elevation and we have the result. I want to filter out that have an elevation that is the elevation has to be equal or less than the current elevation plus 1. We can always go plus 1, but we cannot go higher. So if a neighbor has an elevation that is higher, bigger than 1 from us, then that neighbor is unreachable. It doesn't matter how close it is. So from this A, B, C, from this B, we cannot go to this Q. It doesn't matter how close it is, because it's way too high. We cannot jump directly. So that is not a reachable neighbor. So this will give us, so this thing filter out of bounds neighbors, filter out neighbors that are too high. So after this, we have some neighbors which are valid. But have they been visited? That is another filter. We can filter out neighbors that have already been visited, because if we are processing this, just a sec, if we are processing this, that means that that neighbor either has as many, this depends really if we are doing breadth first search or depth first search, but I'm gonna do something like this. So if that, I want to have two conditions here. So we have two options. For example, we have the value, yeah, we have, let's say these are the results. We can get to this point in 5 steps, and there are some other numbers here and here and here. Those don't interest us, and this has never been visited, this has never been visited, and we are able to get to this in 4 steps. Is this thing interesting to us? Not really. Because if the minimum that we can get to here in these 5 steps, we will not improve the value of this. We already know a way to get to this in 4 steps. So if we are going through the 5, for example, some kind of did this way, and then we go to the 4, this 4 will only become a 6. That is not good. So we just increased the minimum number of steps. And we already know that we can get it in 4. Why would we go with 6? On the other hand, these two were never visited, so they are interesting. So even if we visit, okay, this is not a neighbor, let's say, let's be honest. So if we can get to this one, we can put it as a 6 because it has never been visited before. So we want the result to be either a -1 or to be a value that is bigger than our current value. Or we want to have a value that is bigger than our current result plus 1. Because if this is a 5, we're still not interested in processing that. And even if that is a 6, we are still not processing because we can at the very best, not at the very best, at the definite, we can just tie what we already know. So we already know how to get to this point in 6 steps, and now we're going to know 2 ways to get to it in 6 steps. Big whoop. On the other hand, if we have an 8 here, then it is interesting. Then we need to process this. We will need to say that this is actually now a 6, and we need to process it. So once we have our neighbors, we will just for off those neighbors. We're gonna set their value to the current result +1, and we're gonna push them in the queue. And with this condition, we can also guarantee that we won't have any backtracking. Because in the fork 5 case, for example, what happened if we basically came to this 5 from this direction? Now if we say, hey, here's the 4, let's process it. And then that's going to say, hey, let's a 5, let's process it. Hey, let's a 4, let's process it. And we're moving into an endless loop. This way, we are limiting which neighbors go into the queue. And we are not allowing the neighbor from which we came to the current position to actually be included. This is a variant of a flat fill algorithm. And let's see if it will actually do something. Let's just say console log results. And return 0. Are not interested in the 0 right now, but I'm gonna just add a console log here. Yeah, just to say we are processing that one. If we see this going into an endless loop, that means that we did something wrong somewhere. We have this. So 0, 1. Seems that we finished and we have our results. We can get to 0, to 1, to 3. Let's see what the result for our end is. And it looks like it's 31. So if I'm correct, this might be our solution. We didn't have to go all the way to get to 31, but doesn't really matter. And I think in this case, we are gonna go all the way through. And we can see that we did visit each of these, which won't be the case for the big input. For the big input, I think that we will be left with some -1s at all. No, actually we can get to everything. But there are some, for example, if we get to this value of a's on this part, we won't be on that part, yeah? We won't be able to somehow to leave that thing because all the walls are C's, which are too big for us to climb out. And we have another one over there, and we have some values of A's that are basically impossible to get out of. Who knows, maybe they play in some role in part B. So what we will need to do, we will just need to return result of n.y n.x. If we are correct, that is what the one we are actually want. The result part 1 is 31. I will just remove the console log so it doesn't do anything. I'll comment it out. We might need it for the big input. And for the big input, we have the magic of copy and paste. We have our start over here and the end over here. And from what I've seen, we basically need to do a few loops around the thing because we have these here and then E, F, G, H, and so we're gonna have to run a few loops across the mountain. But let's see if that is. Oh, I haven't saved this one. It says that we have 408 steps required to climb the mountain. Let's see if that is correct. 408 steps. That's the right answer. So I'll simplish flat fill solution made the cut. As you walk up the hill, you suspect that you want to turn this into a hiking trail. The beginning isn't very scenic, though perhaps you can find a better starting point. So start as low as possible. What? Aha. Hmm. We need to see fewest steps to reach this goal. Ah, got it, got it, got it. So now we don't have a start per se. We have a lot of starts. So I will. I don't need this, but I will extract this into a method. Since I'm not using the pack, I'm gonna remove this. We just need the maze. And we're actually gonna deconstruct it here, so it's gonna be a start, an end, and a map. We can call the map a maze, actually, but okay, we started it this way. So for a given start and end, this could be wasteful. I have a feeling that from a single computation of the result, I could somehow eke out what the result should be. So in this case, I'm gonna say find path of input, then return that. So part 1 is simple. But for part 2, let's see if this is still returns 408. Yep, 408. But for part 2, I will just say from the input, from the map of the input, yeah, map.map. This is not a very good. And for each row, I'm just gonna get a list of possible starts. And the possible starts are basically the ones when the cell value is 0. So I'm gonna say row filter not filter, row.map, each cell, and this is the cell value, this is a simple number, to an object which will be cell each value. Let's not call this cell, which will be each value and an index. Map it to an object that has the value and the row. I can write this, but it's gonna be very complicated. So let's write it this way. For loops have the better characteristic that they sometimes can be cleaner. So const ace is an empty array. Ace will be our array when we are storing all our possible starts, all the possible values of A. So we're gonna loop through input dot map dot length. This is gonna be the Y index, and we're gonna have a row which is our input dot map of Y index, and then for each X index we can get the element, and this is exactly what I want to do. If the value is 0, then we're going to push the X index and the Y index as a possible starting point for our whatever, for our trail. Let's see if this will work. Yes, let's start it and see what we will have in the AS column, in the AS variable. If we are correct, the AS variable should have this field, this field, this field, this field, this field, and this field. So we have 6 different options for the start of the trail. NAS has 6 different options for the start of the trails: 0, 0, 1, 0, 0, 1, 0, 2, 0, 3, 0, 4, and that's all we needed. So now we can, for example, say, well, as.map each element, that's each A location, to basically this method. Find me a path from A to the end using the given map, and this will return any. What do you mean it will return any? Result is should not be an any array. Result should be a number array. So we have that find path returns a number. Oh, and find path that it returns a complete maze. Let's change that. Let's say that find map returns a start, which is a actually, who cares? It will work either way, but let's do it that way. So find path will receive separate parameters, not a single object. It will receive an end, also this, and it will return. And now I'm gonna rename this. It's gonna be called maze because maze is the better name, and that's gonna be a number matrix. So instead of maze map, we're gonna say maze, maze, maze. So it's not gonna be find path of input, it's gonna be find path of input, input style, big whoop. Actually, since we're going that way, we can do our destructuring here. Yay. And if we do the same thing here, because right now we don't really care about the start, I'm gonna use this. Because we are treating every A as a possible start, and the start is just one of the A's. So we are mapping all of them, and now we need to take care of one thing. So I will just sort them by size and then return the biggest. Yeah, return the slowest, the smallest. And if I'm correct, this will return, in this case, the correct value. Yeah, I messed up the type somewhere. Where? Ah, part 2 is returning trail length. Oh, yeah. It actually gave me a suggestion to use this, and I said, no, I don't want that. I actually do want this. Now we have another error. Where is it? Yeah, when we're destructuring, we can just say we're not even getting the start. So it says 31 and 29. And if we see, our results are 31 and 29. But I have a distinct feeling, because of those pockets of A's that I saw earlier, that it will give me the wrong answer for this. Did I save? Yes. Yep. It told me the answer is -1. Why is that? Because in this case, when we have on the bottom right corner, these A's, here, they are basically a dead end. Because if we start from here, we can go through all of the A's and that's it. And there our queue runs out of elements because we run out of neighbors which are proper. And everything else is just unreachable. And unreachables are, we said that the unreachables are -1s. So one way to do this would be to filter this to say that after we map it, filter out the -1 because those are the unreachable ones. But on the other hand, we are only using the -1. That's a magic number that we are using here. And I'm gonna instead use number positive infinity. Yeah. And actually that will simplify this condition as well, because positive infinity is the higher number than the current number of steps. However many steps we have, even it's a million, doesn't matter if we add one to it, it will still be less than the positive infinity by the definition of a positive infinity. So I will return the smaller input just to verify that this actually works. We are looking for 31 and 29, I guess. Yep. So now let's see what does it say for the bigger input. It says that 399. And note that the slowness of this approach. Let's just verify that this is the correct answer. Yes, it is. I mean, of course it is. And for the first time in a while, we have a full set of stars. That's great. And we are basically halfway there. We have solved the easiest part of the advent of code. So from now on end, there will be some scary tasks. But let's just for a second look at the timings on this. We have 7 milliseconds for the input because it's simple, and 30 milliseconds for the first part, but almost a second for the second part. Why is that? Because the way that we are solving this, we are basically rerunning the first part for how many A's are there. So if I say find me an A, and it says we have, if I say AA, 40 places, 29 places, 19 places. Yeah. We have 991 A's in this matrix. There is a lot of A's over here, and most of them are not even good candidates, so to say. Almost all of them, I think, will be dead ends. But doesn't matter. We will re-solve the task for each and every one of them. We are fundamentally throwing away everything we deduced so far and starting anew and anew and anew and anew, and we're constantly recalculating all the items. But on the other hand, so this solution is not a good solution because it's extremely wasteful, but on the other hand, is not so slow. So we'll see how the other tasks go. If we have a chance, we will definitely try to revisit this and somehow optimize it. And speaking of optimization, let's run one more thing. Let's run all the tasks that we have so far. That's up to 12. And this is from last year, the name for task 7 last year. Let's see if we have it like this, and we need to take solutions up to L12 because we still don't have anything else. Let's see, run all. What will run all do? It's kind of slow to start up, but relatively fast to go. Yay, we have this, and we have some kind of an analysis. So for now, this time it was even slower. 37% of the time was spent on the task number 11, on the day 12. 15% was spent on day 11 and 11% was spent on day 4, and everything else is relative to this. So yeah, so far task 12, the total runtime is 2.5 seconds, but 2 3/4, but so far it seems that the task 12 is the prime candidate for optimization. And of course, on the other hand, we do have what to optimize. We know that we should calculate something around that. Yeah, now it's 53%, but the percentages will fluctuate, but they will generally stay the same. You can see which of the tests are extremely fast, which are extremely slow, and we have some inkling on what we should optimize. So that's it for today. Like and subscribe this video if it was interesting for you. I know it was interesting for me, and talk to you tomorrow.